Hello everyone, my name is Ashley Blackwell and today I'll be presenting on my project entitled Early Detection of Coral Bleaching Using Surface Enhanced Raman Spectroscopy. So as an outline for this presentation, I want to half of it give the background behind what coral bleaching is, why it occurs, and where the gap in knowledge in this field can be found. And then I want to give you the theory behind Raman spectroscopy, how it can be converted to surface enhanced Raman spectroscopy, and why any of that matters and can be applied to the coral bleaching itself. Then I'll talk about the research aims, which is developing nanoprobes for sensing hydrogen peroxide in ocean water. And then we'll talk about how we can apply that quantitatively to detecting the coral bleaching event. So first I wanted to give a little bit of relevance using this graph that the EPA has provided, which is simply the rise in temperature of the ocean over the last 100 or so years. So this graph shows the steady increase, and as we know, due to the global warming crisis, as we see a steady increase in this temperature, we see the coral begins to bleach. And so the EPA also projects that within the next 200 years, we'll see almost 90% of coral species extinct due to this global warming crisis. So what exactly causes coral bleaching? And so we know, based on what I've said about the global warming crisis, that high temperature and ocean acidification are two of the leading causes for the coral bleaching. But what is actually occurring here? So coral and algae live symbiotically. The algae provides nutrients to the coral, and the coral acts as a place for the algae to live and be protected. But whenever we experience this high stress event of the rise in temperature and acidification in the ocean, we see the algae produce reactive oxygen species. This reactive oxygen species is released into the ocean water and mixes to create hydrogen peroxide. The hydrogen peroxide damages the coral, and because of that, the coral will expel the algae in a response. This leaves the coral vulnerable. And that is when we start to see the bleaching event where the coral begins to completely turn white. And so that's a little bit of background behind what coral bleaching is. And so now I want to move into the characterization technique that I'm using to detect this coral bleaching, which is Raman spectroscopy. So just a little bit of theory behind it. Professor C.V. Raman in 1928 discovered that there was a second type of light scattering opposed to Rayleigh scattering, where the energy that is incident upon a molecule is the same amount of energy that leaves. In Raman scattering, we have the energy leaving being more or less than the incident energy. So what we can do is we can measure the difference of energy that was incident upon the molecule that left the molecule after the vibration occurred. And based off of that, we can measure its position in inverse centimeters, and we can attribute that to specific functional groups and use that to characterize compounds. And so that's what you see here to the left, a little table of different positions on the Raman shift spectrum and how that can be classified for each functional group. So that's Raman spectroscopy. Unfortunately, that only happens in every 1 in 10 million photons. And so what we need to do is include metallic nanoparticles in order to increase the magnitude that we are enhancing the signal given off at that characteristic Raman shift. And so we use those theories and we move on to our research aims, which the aim 1 is to develop nanoprobes for sensing the excess hydrogen peroxide in ocean water. And so to do this, I simply took a gold nanostar and attached dihydrorhodamine dye onto it, which is a non-fluorescent dye. However, whenever it's in the presence of hydrogen peroxide, it oxidizes and turns into rhodamine dye. Rhodamine dye, as you can see in the bottom left-hand Raman spectra, gives off characteristic peaks. We can look for these characteristic peaks and determine whether or not hydrogen peroxide was actually in our sample. So aim 2, how can we apply this to determining coral bleaching? So, because coral bleaching gives off the excess hydrogen peroxide in the ocean water surrounding the coral itself, we can create these probes and we can put it in a solution with hydrogen peroxide present and hydrogen peroxide not present. And as you can see here on the bottom of this illustration, this is what we will see. So, if the hydrogen peroxide was present, indicating coral bleaching, we would see the characteristic peaks of the rhodamine dye. If not, it will remain dihydrorhodamine dye attached to the nanostar, and we will not see any signal at all. And so this can be streamlined into a kit using a handheld Raman spectrometer to use in field to sample water surrounding coral, and then test that water with incubation of our nanoprobes to see if we receive the signal of hydrogen peroxide or not. Thank you all for coming and listening to my presentation.